Hi, I'm Chuang from Newcastle University. I'm happy to introduce our study about tracing the movement of a landslide in Bolivia with 5-year Sentinel-1 data. Actually, in this study, we not only use INSAR but also use geophysical observations to analyze both the surface and subsurface characteristics of the landslide. As we all know, INSAR can be used to monitor landslides in long term, with the advantages of large-scale area covering and high time resolution, but INSAR cannot directly obtain landslide subsurface information such as depths. Borehole and field investigation are always needed to get such information. Geophysical observations such as a dense network of seismic noise measurement can also be used to infer for the depth of the landslide by using HV technique. The technique analyzes the spectral ratio between the horizontal and vertical components of motion recorded by a single seismic station. In our study, we jointly used INSAR and seismic noise measurements to investigate a landslide in Bolivia. The landslide is located at Villa de Independencia, a municipality in Bolivia. As shown in the pictures, there were already observed cracks in the downtown walls and wall collapse, but the local community lacks ground monitoring. Here we collected Sentinel-1 data from 2015 to 2020 and processed them with gamma and stamps. We also had a field investigation in 2017. During the investigation, as indicated by the green dots, there are 120 seismic stations set up to collect seismic noise measurement, and they are processed by HV techniques. Okay, here's the results. With the INSAR observations, we can clearly find that in the study area there are three landslide sub-blocks: town center, upper block, and east block. The town center and upper block have different sliding direction, and they are separated by a road across the town. And the east block are separated with the other two blocks by a ridgeline. We further simulated displacement along the slope and projected them to the descending and ascending loss. We can see that inside observations and simulations have similar spatial pattern in all the three subblocks. This means these three subblocks move individually following their slope direction. Here is the results of HV amplitude curves. The results are related to the landslide depth. The horizontal axis of HV curves is the frequency of the soil. The smaller the frequency, the deeper the landslide, the sliding surface. The vertical axis is the HV amplitude. The high amplitude means the characteristics at this depth is considerable. So based on the HV results, we computed and interpolated the depth of the entire landslide, and then the volume of the landslide can also be calculated. Okay, after analyzing the spatial distribution, let's take a look at the temporal behavior of the landslide. Here, the loss displacement has been projected to the slope direction. We can see from the figure that all of the three subblocks have 2 times of acceleration after 2018, and the town center has the largest acceleration. If we compare the acceleration with the precipitation, we can find that the time period of acceleration corresponds to the increased precipitation in the late rainy season, as indicated by the green shading. Okay, here's the conclusion of our work. INSAR and HV measurements are jointly used to characterize the landslide motion. and 3 landslide subblocks were identified, and the acceleration of the landslide since 2018 is revealed, and it is triggered by the increased precipitation in the late rainy season. Okay, here more details can be found in this paper. Thank you.